What I'd like to do in this video is introduce you guys to a neat little application of geometric algebra called the Kepler Problem. Now the Kepler Problem asks the question, what is the motion of two bodies because of gravity? Now what we're going to do first is set up the problem, make it mathematically precise, and discover the equation that we're going to have to solve. Then we're going to talk about two very important conserved quantities of motion. First, angular momentum, and secondly, energy. Let's get right into it. So let's say I have two masses, m1 and m2. What I'm going to do is first set up some vectors. Let me pick an arbitrary point, let's say right there. I'm going to draw a vector from that point to mass 1. Let me call that displacement vector r1. And I'm going to do the same thing for m2. I'm going to define the second displacement vector as r2. And what I'm going to do is join the tips of these two vectors, like so. So this is going to be a vector from mass 1 to mass 2, pointing to mass 2. I'm going to call this vector r. And hopefully you can convince yourself that this relative displacement vector r is equal to r2 minus r1, just through simple vector addition. To make this situation a little bit less abstract, perhaps you can think of m1 as the sun and m2 as the earth. And r is just this relative displacement vector pointing from the sun to the earth. And what we're going to do is attempt to describe the evolution of this vector r. Now the next thing I'd like to do is use Newton's second law on m1 and on m2 to describe the accelerations of the vectors r1 and r2. So Newton's second law is going to say that the acceleration of r1, which I'll notate as r1 double dot, is equal to the force acting on mass 1 due to mass 2 divided by mass 1. And we have a similar equation for r2 double dot. We have that r2 double dot is going to be the force acting on mass 2 due to mass 1 divided by mass 2. Now by Newton's third law, we have a special relation between F12 and F21. We know that they're going to be equal and opposite. So mathematically what that says is that the force acting on 1 due to 2 is equal to the negative of the force acting on 2 due to mass 1. What I'm going to do is substitute that right into this equation immediately, and I get that's minus F12 over m2. By the way, these dots up here are indicating time derivatives, as they usually do. Now what I'm going to do is I'm going to write down what F12 is. So F12, this is a vector quantity. So I'm going to have to tell you what the magnitude is, I'm going to have to tell you what the direction is. Now F12 is given by the Universal Gravitational Law, and the direction for the force of gravity is going to be in the line joining the two masses. So what I'm going to do is I'm going to define a unit vector, a vector of length 1, in the same direction as r. I'm going to call r hat. So the gravitational law says that the force acts in the same direction as r hat, and the scalar out in front is going to be g m1 m2 over r squared. And r is going to be the length of this vector r. This is going to be the distance separating the two bodies squared. And g is universal gravitational constant. Since I know what F12 is, and I have equations relating F12 and both r1 double dot and r2 double dot, I'm all set. So let me substitute those right in. So I have that r1 double dot is this quantity divided by m1. And what that means is that that m1 right there is going to cancel. So what I'm left with is that r1 double dot is equal to g m2, because the m1 cancels, divided by r squared times r hat. So what that's telling me is that the acceleration of the vector r1 is in that direction. It's in the same direction as r hat. It's going to be a scaled up version of r hat. And let me do a similar thing with r2 double dot. And I have that r2 double dot. Since I'm dividing by m2, this time the m2 is going to disappear here. And I'm going to have to throw in a minus sign. So what I'm left with is minus g m1 over r squared times r hat. Now here notice that I have minus r hat. So that means the acceleration of this vector is going to be that way. It's going to be in the opposite direction as r hat. Which makes sense, right? m1 is going to accelerate that way, and m2 is going to accelerate this way. Next, what I'm going to do is I'm going to return to r, which is that relative displacement vector, r2 minus r1. I'm going to take two time derivatives, and what I'll find is that taking two derivatives of both sides is that r double dot is equal to r2 double dot minus r1 double dot. So what that's saying is that the acceleration of this relative displacement vector r is equal to the difference of these two accelerations here. And since I know what these two are, let me just subtract the two. So I'm going to have to take this thing and subtract away this. And what I'll find upon doing that subtraction and doing a little bit of factoring is that I'll get minus g times the sum m1 plus m2 over r squared times r hat. And for my last little simplification, what I'm going to do is just define up a new constant, which is going to be g times m1, m2. So what I'm going to do is I'm going to take out this g, m1, m2, and I'm going to call that mu, which is, I guess, called by people the gravitational parameter. It's actually the sum of gravitational parameters of m1 and m2, but this will just be a new constant mu, which is going to allow me to write this in a more notationally compact form as minus mu over r squared times r hat. And this is really the equation that we're going to be dealing with in the next few videos, and we're going to be philosophizing about. Let's make sure we understand what this equation is saying about the acceleration of r. It's saying that r double dot is some negative number times r hat. And what that means is that this vector r accelerates in a direction opposite to r hat. So it accelerates that way, which makes sense because from the perspective of m1, the force acting upon m2 is always in a direction toward m1. So if the forces act toward m1, by Newton's second law, the acceleration should also be in that direction. As I said, this is the main equation that we're going to be dealing with. But let me put this equation on the back burner and talk about angular momentum for a little while. Let me first talk about how you normally talk about angular momentum. Let's say I had some mass m, and I had some arbitrary point over here, maybe some origin, and I draw the displacement from the origin to the mass, and I call that the displacement vector r, as I have been doing. Let's say the mass is in motion, and let's give it some velocity, and I'll write that as r dot, the first time derivative of r. Now, what you normally do is you say, let's have the angular momentum, which I'll call L, be equal to r crossed with the momentum, which is the mass times r dot. So you're going to take the cross product of this vector with m times this vector. And using the right-hand rule, what you'll end up getting, in this case, is a vector pointing out of the page. So this would be the vector L. It's actually a pseudo-vector, but we'll leave that aside. And you might also write this as r crossed with p, where p is just m times r dot, the linear momentum. That's all well and good, talking about this angular momentum pseudo-vector. The only problem is that if we want to talk about motion at a plane, to start invoking this angular momentum concept, because we're using the cross product, it seems that we have to invoke a third dimension, where it's not obvious that you need a third dimension to describe this angular momentum. Because remember, the cross product only works in 3 dimensions. It makes no sense to talk about a cross product in 2 dimensions. Now what I'm going to do is talk about angular momentum from the point of view of geometric algebra. What I'm going to do is I'm going to define the angular momentum, which I'm going to call h, because it's going to be the angular momentum per unit mass, as you'll soon see. So h is going to be defined as the wedge product between r and the velocity, r dot. So the wedge product between this vector and this vector. So remember what the pictorial interpretation of this is. Taking the wedge product of this vector with this vector, we draw in that parallelogram using those 2 vectors as the sides. This is an oriented area. The magnitude is given by the amount of area here, and the orientation is going to be counterclockwise in this case if you check the direction, if you check the order, r and r dot. But you can see this also describes this angular momentum concept just as well, and there's no need to invoke any third dimension. You don't need to invoke some dimension orthogonal to the plane. And hopefully you can see that because we got rid of that m there, that this is actually, that this h thing is the angular momentum per unit mass. Let's return to our gravitational problem, and we'll start using this angular momentum concept and see what we get out of it. Remember that r is just that relative displacement vector from m1 to r2, for example, from the sun to the earth. And r dot is just the velocity of that vector r. And let's explore a little. Let's take the derivative of h, that bivector. So it's going to be d dt of r wedged with r dot. And we see we have a product here. So if we're going to take the derivative of the product, let's just go ahead and use the product rule. Be a little bit bold here. So I'm going to take the derivative of the first factor. So it's going to be r dot. Leave the second factor alone. Plus, leave the first factor alone, take the derivative of the second. So I get r double dot. We have a vector wedged with itself. That's always 0. So we're left with this r wedged with r double dot. Now, remember what we were saying about this r double dot here. If we consider that unit vector r hat, this equation is saying that r double dot is in the exact opposite direction as r hat. So r double dot might look something like that. So what happens when you take this r and wedge it with this vector? What's the area of the parallelogram swept out by those two vectors? Well, that's 0. So actually we find that d dt of this quantity, this angular momentum per unit mass, r wedged with r dot, the derivative is equal to 0, which is saying that this quantity is conserved throughout motion. So r and the velocity can be changing over time, but if you wedge these two together, it's always going to give you the same bivector. So actually we have a conserved bivector quantity. This is a famous physics concept called the conservation of angular momentum. What I'd like to do now is tie in that conservation of angular momentum with a very famous physics fact called Kepler's second law, which is that equal areas in equal times law. So here's what I'm going to do. We're going to consider that m2, and we're going to consider that relative displacement vector r. And what I'm going to do is I'm going to suppose this mass has some velocity. Let's say the velocity is in that direction. So that's r dot. And what I'm going to do is I'm going to consider an infinitesimally small amount of time. And I'm going to multiply that by r dot. So what I get is actually a tiny vector from here to there. So this is going to be r dot times dt. And this vector describes how this mass moves over this small time segment. So the mass is going to move from here to approximately there. And then I'm going to join those 2 points. And what I'm going to ask is, what is the area swept out in that little time interval? What's the area of that triangle? Well, what I know is that if I were to take r and wedge it with r dot dt, I would get the area of the parallelogram, which is going to look something like this. So let me say that again. I take the wedge product of r with r dot dt, and that gives me the area of the parallelogram. So what that means is that the area of this triangle is actually 1/2 this quantity. And I'm going to call this small change in area swept out over time dA. So this is a small amount of area given by 1/2 of this wedge product. And what I'm going to do is divide both sides by dt. So I have the time rate of change of the area, which I'm also going to call a dot, is given by 1/2 r wedged with r dot. Now, what we just found is that this quantity, r wedged with r dot, was a conserved quantity. It's just a constant, which we'll just call h. So we have that a dot is equal to a constant. So another way to visualize this is that if I were to make a graph of the area swept out in an orbit over time, let's say this is time and this is a. Let's say at time equals 0, you have 0 area. The plot of this thing, since a dot is a constant, that means I have constant slope. This plot is just a line. And what this implies is Kepler's second law. Over equal times, you sweep out equal areas, no matter what the orbit actually looks like. And I encourage you to think about this conservation of angular momentum and Kepler's second law in the context of probably what you already know, that the gravitational law generates circles and ellipses as examples of orbits. So think about what this means for the way the velocity changes as you move closer to the sun or further away from the sun. Or you don't change your distance with respect to the sun. So we've seen that this angular momentum per unit mass, r wedged with r dot, is a pretty useful bivector concept. And what I'd like to do is do a little manipulation, since we're going to need this little manipulation for future videos. What I'm going to do is I'm going to remember that the unit vector r hat is generated by taking the vector r and scaling down by its magnitude, which I just called r. I'm going to rearrange this and just say that the vector r is equal to some scalar r times r hat. I'm going to take this expression here and substitute it into that first factor in the wedge product. So I have h is equal to r hat wedged with r dot. So I'm going to take the derivative of this thing over here. So it's a product, so I'm going to have to use a product rule in this thing. So what I have is r dot times r hat plus r times r hat dot. Now, if you think about this expression, this is just saying that the way you can change this displacement vector is move either in the radial direction or tangentially. Now I'm going to take the wedge product here. I'm going to distribute this thing to both terms. Now notice here that I have r hat wedged with r hat, and that's going to go to 0, which means the only term that's going to survive after this wedging is going to be this thing wedged with this thing. So what I'll have is r hat wedged with r hat dot. What I'm going to do next is I'm going to move this scalar to the front. So I have r squared r hat wedged with r hat dot. Now I'm going to remember that the geometric product between r hat and r hat dot, so let me write that over here, r hat dot is equal to the dot product between those two vectors plus the wedge product between those two vectors. So I see the wedge product over here. So if I just subtract both sides by this thing, I can rewrite the wedge product as the geometric product minus the dot product, r hat dot r hat dot. Now what I claim is that actually this second term is going to disappear. These two things are going to dot to 0, and we're going to be left with just this first term. But let me show you why these two vectors are orthogonal, why they dot to 0. And this is going to be a little trick that we're going to discover once again when we talk about energy. So let me move that over here. R hat dot with r hat dot. And here's the little trick. I'm going to interpret this quantity as being a result of taking a derivative of another product. So here's the insight. That this thing is 1/2 ddt of r hat dot with r hat. That is, I'm interpreting this thing as coming from a product rule, actually 1/2 of that. Now why is that? If you take a look, taking the derivative of this thing, you get a dot there, and then in the second term you get a dot there. Remember, the dot product is commutative, so actually those two sum to 2 times this quantity. So that's why you have to scale down by 1/2 to set these two equal. But what is r hat dot r hat? That's just equal to the magnitude squared of r hat. Now over time, that magnitude doesn't change, so that's always equal to 1. And it's equal to 1 because it was that unit vector. So this is actually ddt of a constant, namely 1, and that goes to 0. So that implies that r hat dot is indeed 0. Those two vectors are orthogonal. So that means I can discard that term, and what I find is that h is equal to r squared times the geometric product r hat dot. So I think that's enough talk about angular momentum. So I'd like you to remember that conservation of angular momentum concept. And next we're going to talk about another conserved quantity, namely the conservation of energy. So let's return to this gravitational equation. R double dot is equal to minus mu over r squared times r hat. And here's what I'm going to do. I'm going to take this equation and dot both sides with r dot, the velocity vector. So I'm going to have r double dot dotted with r dot is equal to, see scalar sitting out here, times r hat dotted with r dot. Now, what I'm going to do is I'm going to recycle that little trick that I employed for that other dot product. I'm going to interpret this as 1/2 the derivative of another product. Now, what is this product going to have to be? It's actually going to be r dot dotted with r dot. Very similar logic as before. When you do the product rule on these two, you're going to get a dot there in the first term. The second term, you're going to get a dot there, but you can always flip those two factors around in the dot product. So you're actually going to get 2 times r dot dotted with r dot. So to set this equal to this, I'm going to have to scale down by 1/2. So it's a very similar little trick. So I'm going to do that for the left-hand side. What I'm going to do for the right-hand side, I'm going to have to calculate this thing, r dot dotted with r dot. So let me do that over here. So I have r hat dotted with, remember what r dot was? That was r dot times r hat, just using that product rule, plus r hat dot. Now, notice that this thing, when it gets distributed to this, is going to cancel out. It's going to dot to 0 because we found that r hat is orthogonal to r hat dot. So I'll just take care of this first term. So what I get is r hat times r hat dot r hat. Remember, that's just the magnitude squared of r hat. R hat was a unit vector, so the magnitude squared is 1. So what we get out of that little dot product is just simply r dot. So I'll write that in there. The right-hand side is equal to minus mu over r squared times r dot. Now, what I'm going to do, let me return to this left-hand side here. Again, I have a vector dotted with itself. That's going to be the magnitude squared of the velocity vector. So just the magnitude squared of the velocity vector. I'll call that what everyone else calls it, which is v squared. And then what I'm going to do on the right-hand side is I'm going to integrate it. So I'm going to ask, taking the derivative of what gives me this? And what I'm going to have to do is integrate this 1 over r squared thing. And if you check this for yourself, that this thing is equal to d over dt of mu over r. Now, why is that? You can just move that constant out, ignore it for a second. The derivative of 1 over r is equal to minus 1 over r squared, but you're going to have to use a chain rule so that r dot is going to come out front. So I just integrate that thing, and I set the constant of integration equal to 0, just for convenience. So I have this equality here. For my next trick, what I'm going to do is move this thing to the left-hand side, and we're going to write ddt. Actually, I'm going to move that constant inside right there. So ddt of 1/2 v squared minus ddt of mu over r is equal to 0. And I'm going to use the fact that the derivative is a linear operator. So I have a derivative of a sum, or really a difference, whatever. That's equal to the derivative of 1/2 v squared minus mu over r is equal to 0. And again, we notice that we're saying that the time rate of change of this quantity here is equal to 0, which is to say that this quantity right here is a conserved quantity. And this time we have a conserved scalar quantity, which means that over time, v and r might change as they like, but if you come back and compute this quantity, 1/2 v squared minus mu over r, it's the same at every point in the evolution of this system. Here I just moved this equation to the top. Again, we have this very special conserved quantity, 1/2 v squared minus mu over r. And being a nice conserved scalar quantity, let me give it a special name called the energy, which I'll denote as E. And actually, this is the total energy per unit mass. If you just check the units on this thing, you'll see that we've actually divided out the mass here. Another way to see that too is if you've already seen what kinetic energy looks like, you're probably used to seeing it as 1/2 mv squared. So we've actually divided out the mass here. So this is total energy per unit mass. And actually, let's define up the kinetic energy and the gravitational potential energy per unit mass. So we're going to look at this first term and define that to be the kinetic energy per unit mass, which is 1/2 v squared. And the second term is going to be the gravitational potential energy per unit mass, which I'll denote as U, which is going to be minus mu over r. So if I make these two definitions, what I can say is that the total energy is the sum of kinetic and potential energy. And again, I emphasize that the kinetic energy and the potential energy might independently be changing over time, but the sun is a conserved quantity. Now, if we think of our orbits, let's say that we have an elliptical orbit, and at some point in the orbit, the Earth moves closer to the sun. And what does that mean for the gravitational potential energy? Well, R decreases, so that means this whole quantity gets more negative. It's a larger negative quantity, which means it decreases. It moves in a negative direction. So in order to keep the total energy constant, the kinetic energy is going to increase, which is probably something you already know. As the Earth moves closer to the sun in the elliptical orbit, it moves faster. V has got to increase. And you can do the reverse argument. As the Earth moves farther away from the sun, R increases, which means U moves in the positive direction, which means that the kinetic energy has to decrease. The Earth has to slow down in its orbit to keep the total energy constant. So I think that'll do it for this video. Now, I realize this video is a little bit difficult, so feel free to leave any questions you may have in the comment section below. And hopefully stay tuned for future videos on both geometric algebra and the Kepler problem, as we dive further into this problem and actually show that the orbits produced by the law of gravitation are conic sections, which will be the topic of the next video. So as always, if you enjoyed the content, feel free to subscribe, leave your angry comments below, and thank you for watching.